Quanti di voi hanno già fatto l'esercizio che abbiamo iniziato la volta scorsa? 0, 0, 0, 0, 0, come dettato. Allora, lo riprendiamo in mano. Ok, allora il piano oggi vediamo la soluzione all'esercizio dell'altra volta. Se spengo le luci va mica meglio. Così. Ok. Allora, vediamo la soluzione all'esercizio dell'altra volta e introduciamo la tematica delle condition variable, che è un altro meccanismo. Scusate, devo parlare in inglese, mi ricordo ora. So we are back to the solution of the exercise that we saw last time, and we move later to the alternative implementation of the synchronization and communication primitives through condition variables, which is something that those of you that are following the advanced operating system course will also see there. Okay? So just to summarize, to remind you what was the exercise last time, let me magnify a little bit the characters. Is it okay? Yes. So that was the problem. We had different sequences. We had two alternative sequences. One was given by A, which is followed only by B, or multiple instances of B, okay? The other one, which was C, followed either by D or by E, okay? Do I need to write it? So it was something like A, followed by B, or multiple times of B, and C, followed by D and E, okay? Simple exercises like that I asked you to solve using semaphores, okay? And this is it. So this is the solution. I don't remember where we arrived the last time. Okay. So okay, so here is our manager, resource manager, okay, which is composed, if you recall, by multiple semaphore, one for each kind of process, A, B, C, D, E, resource, sorry, and you have a counter here about the number of blocked processes which are around, okay? Number of blocked processes. And then you have just one counter for counting the number of instances accessing B which were allowed to enter the resource. So, reading the problem, we know that the only resource which may be concurrently accessed may have simultaneously active multiple processes accessing it is B. So B is the only resource for which it makes sense to bring a counter, okay? Counter on the number of executing processors. The other one just have resource free or resource busy. Okay, so you don't need any additional counter. The counters are implemented already by synchronization semaphores, okay, which are 0 or 1. Okay, and then you have a state. Okay, in which state are you currently in? The initialization part, of course, as usual, will have the mutex initialized to 1. Okay, and we have the semaphore, synchronization semaphore initialized to 0. All the counters are 0, okay, and the state is no sequence. I did not start doing anything. I'm covering probably. Okay, better this way, right? Okay, so the state is no one is executing. Okay, semaphore, synchronization 0, counter 0, and so on. Okay, let's start. What do I mean with start A? This is the invocation of the function that should be called every time you need to access resource A. So every process that would like to access resource A, okay, first call this function. Okay, what does this function do? So it acquires a mutex, which is released here, okay, and in the typical way we use private semaphore. It was the first implementation that we saw. Okay, I may potentially block on my private semaphore. Okay, private semaphore as A is only blocking for A. Okay, no other B, C, D, E process may block on the very same semaphore. Okay, and before blocking, make sure you release the mutex. Okay, so what happens here? So when I'm allowed to access A, when I'm allowed to enter here, am I allowed to enter A if there is a B executing? No. If there is a D or C or E executing? No. If there is an A executing? No. The only way I'm allowed to access A is if no one executes. If no one executes. So if no one executes, then I'm allowed to access A. Okay? So this is the condition. If I'm allowed to access A, then my state becomes sequence A. So A is executed. So this is a state that I keep track of. Okay? And then I do the pre-release, so the preventive post of the blocking private semaphore. Okay? So since I'm allowed to enter, I move to sequence A, I do the preventive post, so that when I'm here, I will just continue executing. Okay? If instead I need to block, then I do not do the preventive post, but I increment the number of blocked threads kind A, okay, at this moment. So CA plus plus. Okay? Notice I'm not keeping track on the number of threads currently active in A. I don't need that. There could be at most 1. Okay? There could not be 3 or 2 or whatever number greater than 1 of active threads on A. Are we fine with that? Okay? This is the acquisition phase for a resource A. What shall I do when I release that resource? This is the chunk of code that is conveniently added at the end after accessing A. I should make sure to wake up, if needed, someone else, and I should make sure to switch to a second mode. Okay? I finish executing A, the state should move from state A to state B, because after A, the only process that can execute is B. No other processes can execute. Okay? I cannot go to sequenza nessuno, I cannot go to C, D, E, no, only B. So, this is when I change the state to sequence B. Notice, always do that within critical section. Okay? This should be executed in a consistent way, with no interferences around. And then it is my duty to wake up all potentially blocked B threads. Okay? It is my duty to wake up the B tasks that are potentially blocked. Okay? If I don't do that, then I may keep having a bunch of B tasks blocked here and no one executes. Okay? So it is my responsibility to check whether there is any blocked B, and if so, decrease the number of B blocked and increase the number of B active. I told you that the only process for which we keep track of the number of active threads is those accessing B, okay? And B++, and give him a private post on his private semaphore, okay? This wakes him up, release the mutex, and I'm done. I'm done for A, okay? Now we need to do the same for B, C, D, and E, okay? Okay, let's think about that. So this is B. What shall I do when starting B? Send wait, send post, blocking on the private semaphore as before. Okay? So when am I allowed to enter my B sequence? I should be in sequence B, otherwise I'm not allowed. Okay? Can I enter B when I'm in sequence A? No. When I'm in sequence nessuno? No. I can only enter when I'm in sequence B state. Okay? This means that at least one A finished executing and is waiting for at least one B to execute. So if I am allowed to continue, then increase the number of active threads on B. Okay? Increase the number of active threads on B. Preventive post on the private semaphore. Preventive post on the private semaphore. Okay? So that I will continue and able to enter. If instead I'm not in sequence B state, I shall block. So I register that the number of block B, okay, increases by 1, and I will block eventually here. Questions?
I meant to be increased the active B in the end of A.
Second?
In the end
of A.
Yes,
we have a B++, right? In the other A, right? Yes, and here you see another one. So your doubt is, do we increment it twice? Is this your doubt, right?
Yes.
Well, no. Why is that? See?
And they don't. It doesn't call start B.
So it depends. So either this is executed or this is executed. Okay? So if I don't block, if I'm a B, okay? I arrive, okay? If I arrive and I'm not in sequence B, okay? I'm a B, I arrive, I shall block. So I don't execute this, I execute this, and I block. Okay? When I wake up, someone should increase this counter, okay? If instead I'm allowed to enter, I'm a B, I'm allowed to enter because I'm already in sequence B, and I'm the one allowed to enter, it's me that should increment that counter. Okay? Is it clear for everyone? This is an important point. Okay? You remember that when I showed you the slides, let's go back to those slides just to understand what I'm meaning here. Solution 1. You remember this solution 1? I said, solution 1, I said that the resource allocation is done both in acquisition and in the release. What do I mean, resource allocation? I mean this part and this part. This is NB++. This is the equivalent of NB++. So resource allocation meaning keeping track that one more thread has been allocated the resource to. Okay? So I'm performing the NB++ both here in acquisition phase, okay, for the B thread itself, but also here in the release phase of a potentially different thread. Shall I repeat? Okay, in this first solution, in the second one, no, but in the first solution, we have the duty of keeping track to resource allocation, so keeping track of the number of active threads on that resource, both in your acquisition phase, and this is fine because I'm thread B, I'm incrementing by 1 the number of B actives. But also in the release phase of a potentially different thread. In our case, it was A, the end A, okay, chunk of code, that did a check if there is some B to wake up and increasing NB accordingly. Okay? So this is kind of a mismatch, you know, you have a different thread that needs to increment the counter of another thread. You don't have that with solution 2. Okay? With solution 2 we don't have that. So we have the only point where it is keep track of where the counter is incremented is here. Okay? As an exercise you can do that home, just rephrasing our solution in a second solution, okay, way. Okay? So this NB++ both appear here in the acquisition phase, but also for those that block, it should be done by the thread that wakes them up. Okay? Other questions? Okay, start B, these blocks, and go on. Now what is missing? NB. First NB, okay? What does NB need to do? Okay, let's think before. So when B finishes, okay, what do I need to do? Okay, always wait and signal, okay? And keeping track that there is a one less B. And for now, everything is okay. But then, who is my responsibility to wake up? Exactly. So A or C. So when B finishes, pay attention, it should check whether it is the last B to execute, okay, whether it is the only remaining B, okay, if it is the last B, okay. In that case, in which case, you need to check whether there is any A or C process waiting for B, waiting to be unblocked. Okay? While B is executing, instances of A, C, D, B, E may arrive. Okay? If there is no other B arrive, I'm the last B, then I need to wake up potentially A, C, D, or E. D or E I shall not wake up because otherwise I would broke what my specification requires. Okay? They cannot execute before C. But A and C, they may indeed execute. Okay? So I shall wake up either A or C. If it is not written in the specification which one shall be given priority to, you are free to do whatever you want. Okay, I can wake up either A or C. Okay, let's see the code for waking up A or C. This is like what I put at the end of resource access B. Okay, so send wait, send signal, decrement the counter. If I'm the last B, okay, wake up either A or C. Okay? Let's check this sveglia AOC function. And this is it. Okay, so if there are blocked threads on A, if there are A pending tasks waiting to access A, then decrease them, the number of blocks A by 1, move to state sequence A, sequence A, and signal them a private post on their respective signal. Okay? So by here, I'm deciding to give priority to sequences AB, okay, instead of CDE. Okay? So first I check whether there is some A and I wake them up. Okay? If there is no one here to wake up, notice I have an else here, okay? If you forget the else, it's a mistake, right? If you forget the else, what would be the problem? Oh, I will ask it later, okay? I will ask you later what happens if I remove the else. So if there is no CA to wake up, then check whether there is some C to wake up, some seconds blocked, okay? If so, then do the same for C. So decrease the number of blocked C by 1, okay? Move to state sequence C, and perform a private post to the blocked C thread, okay? If there is absolutely anyone else, then move to sequence nessuno, okay? If I'm finishing B and there is not any pending A or C to deal with, I simply move to sequenza nessuno, okay? Which is the one that allows me to execute either A or C. Okay? So the question I made you before, what if I forget this else? What could be the problem if I forget this else?
This could wake up A and C together.
Exactly. This could wake up both an A and a C, which are both pending here. And in that case, the two sequences, this one and this one, would not be mutually exclusive like it was specified in the program specification. Okay? So you need to put there an else. Okay? I shall not wake up two sequences simultaneously. Okay? Pay attention to this subtle problem. Okay? Everything clear about the end of A and waking up either, the end of B and waking up either A or C. Okay, now let's move to start C. I mean, you probably understood, right, the philosophy behind it. Okay, now let's start C. When is C allowed to start? When is C allowed to start?
When there's no A.
When there is no one executing, okay? When there is no one executing. So if stato sequenza nessuno, there is no one executing, then it's my state. It becomes sequence C, okay? Preventive post, otherwise I record that I've been blocked, okay? Release the mutex and block, okay? When I'm here, what is my responsibility to do? You tell me. Say again? Either or, exactly. I shall wake up either D or A, not both, okay? Not even multiple instances of D, not even multiple instances of E, okay? I shall wake up either D or E, okay? So, let's see if this does that. So, some wait and some post at the end. So, if there is a D pending, blocked, a D blocked, if there is a D blocked, wake him up. Okay, one block less, sequence D, and post on the private semaphore of D. Okay? Otherwise, if there is an E pending, do the same for E. One less E blocked, sequence E, and private post to E. Okay? What if there is not this and not this? What do you expect here? Huh? It depends, okay? Okay, either it depends on the program, okay? What does the specification say? Is D or E mandatory to execute after C or not? If there is no one pending, I can just go back to sequenza nessuno, okay? I'm not sure that it's sequenza nessuno after C, okay? It depends on the specification. If the specification says that after C it is always either D or E, then it shall not be sequenza nessuno, okay, after C. Otherwise, what can happen with sequenza nessuno? That again another C execute or an EA execute, okay? So pay attention to what you put at the end, okay, because it depends on the specification you have in the program, okay? Since the specification says that after C it shall execute either D or E, you cannot go to sequenza nessuno. You can go to a different state, which is called, for instance, we decided to call it D or E state. This is a state that represents the system being waiting for an arrival of D or E.
In that case, I cannot create a new instance of D or E. Is it right? Or?
It's not me, it's not my responsibility of creating an instance. I'm just the manager, the resource manager. It's someone else that creates these instances. I'm just the interface, I'm just the manager of it, you know. So I'm just the preamble and the postable of this access to resource A, B, C, D, E. Okay? So it shall not be me creating, Okay? It's upon me waking up potentially block instances. Other questions? So, this is the state that I created to denote that I'm waiting for any instance of D or E to become available. Okay? What do we expect? We did not yet see what happens for start D and start E. But I guess that in that case, I will see that if I'm in sequence D or E state, then one of them is allowed to execute. Okay? So, summarizing, here we said, if there is an E, a D already, unblock just the D. If there is an E instead, then unblock just the E. If there is no one, enter a state in which you wait a D or a E. Okay? And release the mutex, of course. Okay? Okay, now the last two. Okay, start D. What does the start D do? Okay, start D, I'm here. Okay? So I can start only if I'm in state D or E. Okay, if C finished. Okay, without waking up anyone else. So if I'm in state D or E, and I'm D, I'm allowed to enter. Then it will be sequence D state, and I will do a preventive post of my private semaphore, okay? A preventive self-posting, if you want. Otherwise, I will block, okay? Release the mutex and block, okay? Typical structure. The same I expect for E, okay? I could even use the same code, almost, okay? Just take a look at E, okay? It's exactly the same code, just I enter sequence E, okay? So it is again, if I'm in sequence D or E, stato goes to sequence E, preventive post, increment by 1 instead the number of block E, and release the mutex and block, okay? So both start D and start E are very similar. What shall I do instead at the end of D, or equivalently at the end of E? Okay, what it is my responsibility to do?
Wake up A.
Or
C again.
exactly. Okay, when this sequence is over, so after D or after E, okay, it is my responsibility to wake up either A or C. Okay, let's take a look at that. So at the end of D, between a critical section, I can wake up A or C, which is what we already saw before. Okay, I can reuse the same function I saw before. So let's wake up either A or C. And I guess that it will be the same for AND E. Let's check exactly. Okay, it is exactly the same for AND E. Yes?
We saw that C, in case there's a D pending, C wakes up the D pending.
Second?
We saw that C wakes up the D pending. Is it right?
At C, at the end of C,
Yeah.
it shall potentially check for blocked either D or E. Okay, so let's go back at the code of AND C, right? And that's it, okay? So this is the code of AND C. I first check whether there is any D blocked, okay, or if there is any E blocked.
Yeah.
Yeah.
But we saw that D and E starts just when the state is sequence D or E.
Exactly, yes.
So in that case, D or E never wakes up.
Ah, good question. Let me think about that. Sequenza E, allora, good question. Let me think about that. Well, I'm waking them up here. So it's me that wake him up. So
Yeah,
okay.
because they...
let's go where the code is. Okay, start D for instance, start D.
Because they've already passed that
Exactly.
that statement. Okay.
Exactly. So they are here if I shall wake them up.
Yeah.
Okay. So this is for someone that just arrives. Okay.
Of course. Yes.
Okay. Other questions? Other questions? No? Okay. So this is it for a semaphore implementation. In the code that I will put available to you guys, there is a follow-up. So it will be the same using condition variables, which is what I will show you guys today. Okay? So there is an alternative synchronization primitive called condition variable, which is similar to the concept of monitors, that I will show you. Okay? It's an alternative solution to the semaphore 1 or semaphore second solution. Okay? It's using condition variable, and it appears right here. I will show you later. Okay? This is the same program solved with condition variables. Okay? I would just like to show you what you know these conditional compilation directives, right? Okay. So I will show you just a typical way that I program this kind of concurrent code. Okay. So tomorrow I will give the stage to Roberto Cavicchioli, which will introduce you to pthreads for those of you who are not familiar with it. So I will just show you briefly how this code is written. Roberto will introduce more deeply on how to use pthreads, what are the creation primitives, synchronization primitives, and cancellation primitives, and whatsoever. Okay. So I'm just showing you the code that I used for like using pthreads to solve that example that I showed. So this is like a function that is useful for like adding some waiting time. Okay, so typically if you create multiple threads, you don't want them to be perfectly synchronized, but you would like them to be a little bit interleaved in the execution. Okay, so I typically use this kind of simple function to add a randomized break, a randomized pause, okay, a randomized sleeping time for each of the threads. Okay, this is like a function called nanosleep that put to sleep the threads for a random one. Okay, these are the threads. Okay, this is thread A. In the pthreads you will see, last time someone asked me why there is a null pointer here. Well, this is the specification of pthreads. Typically, when you will see with Roberto, but typically the threads can be merged, can be joined, and maybe you are waiting for a thread to complete, and this thread that is over is able to return back to the waiting thread, to the thread in which he merges, in which he joins, to return back some results. Okay? Since we do not want to specify in general any kind of data type, we just use a general pointer, a void pointer, to specify that that thread can return whatever it wants. Pointer to something. Okay? This is what that thread, when it joins, may return to the joined thread. Okay? So you will see better in Roberto's explanation, but for now, this thread, what it simply does is forever trying to access A. Okay? So forever, I just start A, I write something just to signal that I was able to access A. For instance, I put an A here, okay? And then end A, which is like the function that we just saw, okay? And then a random sleep. This I told you, not just to make it continuously working, but adding some random sleep, some random pause, a random break among two different instances of the same thread, okay? I remember I told you in the first class about real-time systems that real-time embedded systems are often concerned not with batch activities in which you have just a lot of workload to execute, and when it's over forever. No, real-time systems are recurring. Okay? You typically have something that is repeatedly executed every period, okay? Or at least every period, okay? Depending on the task model that you use. We will see that in the theoretical classes. So here, it more or less resembles this kind of periodic behavior, okay? Every now and then, this guy will reactivating, trying to access, okay, the resource A. This nano sleep will essentially deschedule it, okay? It's sleeping, and it wakes up again here, okay? It's a simple way to implement that. There are other ways for which you can implement that. For instance, hooking it to a timer or whatsoever. B does exactly the same thing, C does exactly the same thing, and so on, D, E, okay? This is exactly the same thing. We just decide what kind of chart to put to signal, okay, that I've been able to enter that section, okay? Let's see the main, in which I shall create the threads. Again, tomorrow you will better see the primitives to do so. I shall create a set of attributes. I shall create the thread pointer. I initialize my manager, okay? I initialize my random number generator, okay? These are the primitives that you use to initialize the attributes of the thread creation. This you will see with Roberto is working on the attributes of the threads that you like to create. The touch state, okay, I will need you guys to first have the class on the thread specification, okay? This is a simple trick to avoid writing 1,000 times the join primitive. And here is the instruction where I physically create the threads, okay? So here I'm creating a thread of kind A, a thread that would like to access resource A. How can I make sure that this guy executed? Because this guy will try tentatively to write in standard output a small a, okay? So this is what he will try to write. Then I create a second thread, again accessing the same resource, okay? That can be multiple threads trying to access resource A, okay? A is a shared resource, okay? And to highlight that that guy was able to access that resource, I make him write a capital A, okay? A capital A, majuscule. For B, thread accessing resource B, I have 3 threads accessing resource B. One that writes a big B, one a small b, and one an X, okay? I do the same for C, creating 2 threads accessing C, creating 2 threads accessing D, creating 2 threads accessing E. Okay, and I shall destroy the attributes, okay, and then I wait 10 seconds and then my program is over, okay. This is the typical way in which you can write example p-thread programs for solving your exercises, okay. Thread using the start A or end A or like a preamble and a postable for synchronizing in the shared resource. Then you have the thread creation. You can create as many threads as you want, and you typically put something in standard output to signal that that thread was able to access that resource. In standard output, at the end, you will have a sequence of characters, okay? If my sequence of characters will be something like A, B, A, B, A, B, C, D, A, B, C, D, C, E, C, D, everything is fine. If I notice something like AD or AC, okay, or CB, something of that kind, it means that your synchronization does not work properly, okay? So this is what you typically do to check that your synchronization behaves correctly. As we said, if I run it multiple times and I never see something strange, it doesn't mean that your program is 100% correct. It just means that the first debugging that you did, okay, no problem was encountered, okay? Of course, if instead you see something like AD, then you immediately have a proof that your program is not working correctly, okay? Proving the correctness of concurrent program is somewhat more involved than just running it for 10 seconds, okay? Are we okay? Good. Let's move back to monitors. Okay, so monitors. As I told you, there is a third way to solve synchronization and consistency problems. You remember we had a first solution in which I did a preventive post in case I shall not block, and I had the keeping track of the number of threads allowed to access the resource both in acquisition phase and in the release phase. Then I had a second solution, which was this one. Where is it? This one. Okay, this is the second solution where we had a somewhat cleaner paradigm in which, just to remind you, okay, since we did not use this paradigm in the exercise, but we had a wait and a signal, which is clean here, and I had here in the release phase this token passing mechanism, which somewhat disturbed us, because you had a wait here on the mutex and a selective post just if you don't need to pass the token. Okay, you remember solution 2 with semaphore, wait, but there is not a signal that's always executed. In case I have someone to wake up, I will pass him the token. I will pass him the mutex so that if he was blocked, where was he blocked? Here. If he was blocked, then he will continue holding the mutex. You shall not allow someone continuing without holding the mutex, because here there are instructions, okay, here there are instructions that shall be executed in an atomic way, in a mutual, exclusive way, okay? You shall not allow a task to continue here without holding the mutex. So the second solution, what it does, it passes the token to the woke up thread. Okay? Well, this is also kind of involved mechanism to do things, to do synchronization. And also we said, what if I need to wake up more than one thread? What shall I do if I need to wake up more than one thread? Okay? I can only pass one token. If I want to pass more than one token, I need to modify something here. Okay? I need to modify something here and recheck again if there is someone else to wake up. Okay? But I need first to retake the mutex. Okay? Well, core written core proposed a mechanism called monitor that allowed us to solve the synchronization problem releasing consistently the mutex. So what it did, it basically, so here was the trick, right? So here we have a post of the mutex before blocking, okay? You remember, this is key because you never want to block while holding the mutex, okay? So he further modified this mechanism, writing a post away and again a post on that very same mutex, okay? So it was something like, when I unblock, I have a post, a wait on the mutex. So I'm unblocked in the private semaphore, but then I will again do a wait on the mutex. So so it goes. So we have, in this paradigm, we have a wait on the mutex, okay, which is this one. And then if I shall block, okay, if I shall block, then what do? Then record the type being suspended, for instance, block the plus plus, okay? and this is the tricky part, and we try. I release the mutex, okay, so I post the mutex, and I block potentially on my private semaphore. Okay, this is what I wrote here, right? In order to continue from here, I told you, I need that at waking up, someone passes me the token, the mutex token. Okay? The alternative, which is what Thor proposed, is to redo a wait on the mutex. Okay? So I retry acquiring the mutex that I released before. Okay? So this, okay, this is a combination of mechanisms, of instructions. So release the mutex, tentatively blocked, and reacquire the mutex is what is implemented with condition variables. See again here, what do I need to implement this bigger instruction? Okay? I need the argument of the mutex and the private semaphore. Okay? And I can do another instruction that basically does that. Releases the mutex before potentially blocking, and before continuing, it shall reacquire the mutex. Okay? This is what we are going to see now. Also, it will not require here all this mess. So, if I'm making sure that the guy that was blocked, when it wakes up, it is his responsibility to retake the mutex, then I shall not do this mess here. I can ignore this, and I can simply release the mutex. Okay? This simplifies very much the things here, okay? It simplifies very much the paradigm. Let's see how is this implemented, okay? So these are monitors. So this is implemented with monitors. These are a language structure equivalent to semaphores. So C and C++ does not have monitor support in the language itself, okay? C and C++ do not have monitors. If you want to check which are the languages that have monitor support, it's Ada, it's C#, okay, Concur and Pascal, Java with wait and notified methods, Mesa is one of the oldest one, probably the first one trying to implement the monitors, okay? And, okay, Python, Ruby, but you don't have that support in C or C++. Okay, you don't have support in C or C++. Okay, so a monitor, again, is a language equivalent of semaphores, but cleaner. Okay, you don't need to get crazy with the semaphore primitives that we saw before. You don't have it in C++ or in C, but we do have library support thanks to pthreads. Pthread is a library. Pthread is not C or C++. It's a library which you can use in C and C++ for achieving thread support. Okay? So with pthreads you also have condition variables, which are a convenient way to implement monitors in C and C++. So what does it do? So it contains variables and provides procedure, okay, to other software monitor in an object-oriented language. Okay, for instance, in Java you do have it. So what does a monitor do? So only one thread can execute a procedure at a certain time. Okay, so the mutual exclusion is guaranteed at procedure level. Okay, so any other thread that has invoked the procedure is blocked. So you guarantee atomicity at procedure level. Okay, so if another thread would like to access that procedure, it is blocked. Okay, and waits for the first thread to exit. Okay, so this way a monitor implicitly provides mutual exclusion. Okay, you provide it at procedure level. Okay, who takes care of inserting in the code all the synchronization primitives that we manually inserted in the semaphore-based implementation? It is the compiler. Okay, So the source code is automatically inserted by the compiler for those languages which provide monitor support. So a monitor support synchronization with so-called condition variable. What is a condition variable? Condition variable is just a blocking queue. It's a queue of tasks, threads that are blocked while waiting on that variables. We do again have some wait and signal paradigm, okay, which are only slightly different to the semaphores one, okay, to the semaphore ones. Okay, again, for condition variable we have cond wait and cond signals, which are almost identical to the semaphore counterparts. Okay, almost identical. So cond wait suspend the calling thread on the queue. Okay, so if I'm not allowed to access that procedure, then I will suspend on the queue, okay, related to that monitor, to that condition variable. Okay. Signal, it resumes the execution of one of the block threads on that condition variable. Okay. Note, there is not any counter in a condition variable. This is the difference with semaphores. Okay. There is not any counter. Okay. You don't have 2, 3, 4. So if I continue doing with semaphore, if I continue posting, you have the counter increasing, like 5, 6, 7, 8, infinite. Okay. Here not. So that if we do a signal on a condition variable with an empty queue, I don't have any counter. Again, I have just a queue of blocked threads. Okay. I don't have any counter that you have instead with the semaphore. Okay. So if I perform a signal, okay, if I perform a post, a cond signal, I will not increment any counter, but if there is some block thread, I wake him up. If there is no one, simply the signal is lost. Repeat. So with semaphore, you remember, if I had a wait, it decrements potentially the counter, while a signal increments the counter. If I have 10 signals together, it increases the counter by 10. If it was 0, it is 10. If it was 2, it's 12. Here instead, the signal, what it does, it checks the blocked queue associated to that condition variable. If there is some blocked thread, it wakes him up. If there is no one else there, it simply gets lost. Okay? You cannot do multiple signals. There is not something as a preventive post like we did before. Okay? Because a preventive post is simply lost here. Okay? There are multiple ways to implement monitors. We will only look at the POSIX approach used with pthreads. Okay, it's the same one used in the Mesa language, which is the original one when it was Prof. So how does it work? So whenever a process blocks on a condition variable, so this is the condition variable, there is always a mutex associated to that condition variable. There is always a condition variable always comes along with a mutex associated to it. Okay? As we wrote here. So what we essentially do with condition variable, you release before blocking the mutual exclusion. This is done by the support of condition variable you encounter at library level. So you don't need to take care of posting wait in the mutex. You just use a cond wait on a condition variable and the associated mutex. Again, when a process blocks on a condition variable, it first releases the mutual exclusion. Okay? It first releases the mutual exclusion. You never block while holding a mutex. Okay? You never hold while holding a mutex. So conditional wait implicitly releases the mutex. Okay? Not only it releases it before blocking, before potentially blocking, but it will retry to acquire it when at wake-up time. Okay? It releases before and it tentatively try to retake the mutex afterwards. So it's exactly what we see here, post and wait. Okay? It's implemented by the condition variable paradigm. Okay? but it has to check again for the blocking condition. This is the important part. Let me try to make you understand why. So here, in this paradigm, with the semaphores, we did, if I'm in the blocking condition, okay, I need to block here, okay? What happens later, we assumed that there is no more blocking condition, okay? Instead, using monitors, using condition variables, there is a subtle difference. I told you, I don't continue right away. Before continuing, after this instruction, I need to retry acquiring the mutex. Pay attention to this point. So I told you, this is my cond wave, okay? That's right, now this is a cond wave, okay? With these two arguments, okay? And this is the condition variable, okay? So, when I potentially block here, I'm unblocked, but it's not so sure that I will execute whatever comes next right away, because I should first try reacquiring the mutex. What happens if I'm not right away able to take this mutex, but someone else took it instead? So, after I woke up, so when I'm here, after I woke up, I tried to acquire the mutex, but someone else took it already, okay? Someone else took it, and it can do whatever it wants. Okay? It may perfectly happen, and it's okay if that happens. Only this other guy executing with my mutex, what can happen? It may happen that this blocking condition changes. So assume that a blocking condition here was should be no writer pending. Okay? Okay, there is no writer pending. Okay, I block. Okay, go the other way around. So there is a writer pending, then I block. Okay? Now I come here, I wake up, because now there is no writer pending, I continue, okay? I wake up, but before taking this mutex, another writer arrives, takes the mutex, and it arrives. And now there is a writer pending again. Shall I repeat? Okay. Remember the reader-writer problem. No reader is allowed to enter when there is a pending writer, okay? So what is the blocking condition in that case? Blocking condition, if there are pending writer, okay? A writer active or a writer blocked, okay? This is the blocking condition, okay? So I block here, okay? With semaphore, when I wake up, with the token passing mechanism, when I wake up, I already have, by definition, I have the mutex. Because the guy that woke me up passed me his mutex. Okay? So there is not this problem. So when I woke up, I'm sure to have the mutex. Okay? Here instead, these are two separated steps. Okay? It is not someone passing me the mutex. It's me when I'm waked up, it's my responsibility to tentatively retry acquiring the mutex. Are you following me? Okay? So what may happen? It may happen that this other guy sends a post to here, okay? I'm potentially able to continue executing. My next instruction will be trying to reacquire the mutex. But between someone posts my private signal and my wait M, another guy may happen. It may perfectly happen that a writer is the first one to acquire the mutex. Okay? A writer is the first one acquiring the mutex. What happens with that writer acquiring the mutex? That it may change again this. So this condition, which is the one that I invented, designed to regulate when I'm supposed to continue or not, is now violated again. What is the outcome? What is the bottom line of these observations that I just made for you guys? That you never use conditional wait with an if. You always use conditional wait with the while. Unless you are 100% sure of what you do. Why with the while and not with an if? Because when waking up, you should always recheck whether the condition, the blocking condition, still holds. How many of you did understand? Raise your hand. Okay, half of you guys, okay? Shall I try to repeat again? Would that help? Okay? So let's redo the example. So, what if I use an if here, or I use a while, okay? Let's see what happens when the writer may come in between this step here, okay? So, I'm a reader, and there is some active writer, okay? So I'm assumed to block, okay? And I block here, okay? I block here, okay? And that's happy, that's fine. Also, I'm the reader, okay? There are pending writer, and I block the here, and I block here. When shall I wake up? When the writer is over. When the writer is over, he will perform a post waking me up, okay? In the talking passing paradigm, semaphores, not condition variable, it will be him passing me his mutex. Okay, so when I resume execution, I resume it while creating the mutex. Okay, no problem. With the condition variable paradigm, which is exactly what you see here, okay, you have a later instruction trying to reacquire the mutex. Okay, so there is no token passing. But without token passing, there is this step here which is critical. It's critical because it may perfectly happen that the writer, what does it do? The writer sends a signal, okay? Sends a signal to this conditional way, okay? So it sends a cond signal. What does this cond signal do? If there is a block thread, and there is a block thread, it wakes him up, okay? Waking this thread up, it doesn't mean that he's the next one to execute. It just means that he's put again in the ready queue. It will be the scheduler which decides whoever executes next. What if there are other writers, for instance, that in this step here arrive? It may perfectly happen. This is not like an immediate execution, okay? This is an unprotected step, okay? This is an unprotected step. Another writer, W prime, may arrive here, take the mutex, and register itself. So it increase V act plus, okay? What if now this guy executes, it tries the M, there is no M, this guy finishes the preamble, okay, releases the mutex, post, releases the mutex, okay, and then starts writing, okay, and then starts writing. The mutex is released, this one retakes the mutex, okay, it may perfectly happen, this one retakes the mutex, and if I don't do the while, it assumes that there is no writer active. It assumes that there is no writer active. Instead, here, I shall use a while, because I shall recheck whether, while I hold the mutex, that condition is or not valid. Okay? Now I see more faces nodding, so hopefully it's clearer now, okay? This is like the most complex thing that we will see about concurrency, okay? This really explains you the lower level details of condition variable, which is something that you don't typically see in operating system courses, okay? So this is to tell you that what the semantic that we are going to see here always assumes a potential mutex release and reacquisition. So you shall never use this with an if, unless you're 100% sure that when you wake up, no one else might have contended your blocking condition here that is protected with the mutex, okay? So it is always better to use that with a while, okay? Okay, instead with semaphore, you are perfectly fine using an if, okay? Because again, the token passing protects you, okay? So condition variables are always used inside a while, okay? So this is not C, this is just a pseudocode, okay? This is like what if you had monitors in C, how would they work? So you would have something like a function a function which is a protected function, so which is a synchronized function, so there cannot be more than one task executing this function. They are always synchronized, so the insertion and the extraction are synchronized on the same monitor. Okay, this is not real C code. Okay, this is not real C code. Conwait and consignals are, but this synchronized is just to tell you what would you do in a language that has this synchronization support. Okay, so you could define different functions that shall atomically execute, they shall sequentialize, that they shall execute in a mutual exclusive way. Okay, so you may typically have something of this kind. This was the circular array example. So while, this is a while, the array is full, conditional wait on the full. Okay, then you do whatever, and if I'm the one that inserted the first element after an empty queue, I will do a conditional signal there. Okay, but notice that the blocking primitive is protected by a while. Okay, so when I wake up here, so if this guy, the extractor, like signals me that there is one less element, so there is one more space to insert things in the circular array, before continuing, I shall retake the mutex. Okay, you don't see the mutex here, it's just the intrinsic semantics of monitor languages, if there is a support of this kind. So if someone else takes the mutex in between, I will need to check again whether the queue is or not full. Okay. So this is the way in which instead we implement it with the POSIX support. So pthreads allow us, besides semaphore and mutexes, also allow us to have condition variables. Okay. But POSIX is an interface, it's not a language. Okay, it's a library that we use. So POSIX program has to explicitly say where a critical section begins and ends. Okay, so this is pthread mutex lock, pthread mutex unlock. Okay, this is not the send wait and send signal. Okay, with POSIX I do not have any language support, but I need to use to explicitly say what is the mutex and what is the mutex protecting. So this is the mutex, this is a lock. It's like a binary semaphore, a mutex, okay? It's like a semaphore 0, 1, okay? No counter in it. So mutex lock, mutex unlock. And the semantic of conwait is pthread conwait. This is the condition variable, and this is the associated mutex. Okay? Again, the mutex which protects the critical section, okay, is used within the arguments of the conditional wait. So the blocking condition on a condition variable needs to specify also the mutex that it needs to release before and to tentatively retry acquiring after being unblocked. Okay? This instruction is exactly the equivalent of these 3 instructions. Okay? So never use that unless you're entirely sure what you do. Never use this with an if. Okay? Because you should always recheck whether the blocking condition still holds after reacquiring the mutex when someone wakes you up. Okay? I repeated it 10 times. Hopefully you guys are okay with it, but feel free to raise your hand if you still have doubts about that. Okay? Even next time, I'm available to explain further. So see again, so while the number, so the array is full, I block. When someone wakes me up, is the array still full? Then I block again. If it is not full again, I continue. Okay? Again, if the array is full, I block. When someone wakes me up, I will try acquiring the mutex. After acquiring the mutex, if the array is still full, I block again, releasing the mutex. Okay? I repeat the third time. I shall block if this is full. Okay? If this is full, I block, releasing the mutex. Someone wakes me up, I tentatively try to reacquire the mutex. If I do acquire it, then this is no more true, I can continue. But if I'm not able to acquire, someone else, for instance, inserted another element, then I recheck this, and I block again, releasing the mutex. Okay? Good. So wake up policies, so this is the preamble, okay, the blocking phase. But waking up policies, this one, okay, the con signal part, these are the wake up policies, allow me simply to wake up more than one thread. You remember with the second semaphore solution, with the token passing mechanism with semaphore, we said that I have problem waking up more than one thread, okay? But with monitor, with condition variables, since we are not passing any token, we can easily wake up more than one thread, okay? As long as we protected this with while, then we are safe to wake up whoever we want. So, here, if I need to wake up more than one thread, I have other paradigms called pthread con broadcast that simply wake up whoever is blocked on that condition variables. Condition variable is a queue of blocked threads, right? I can wake up with a signal one of them, or I can simply wake up all of them. Or I can wake up two of them, or three of them, or all of them, okay? No problem with this semantic, to wake up more than one thread, okay? Okay, so home, I ask you guys to implement the reader writer problem with monitors, so with condition variables instead. You just follow the previous solution, which is this one. This one is the previous solution, which used semaphores, okay? Try to rewrite it using condition variables, okay? You will be using one mutex, okay? You will be using condition variables with the weight specifying also which mutex and signal specifying also which mutex. Notice that you may want to wake up more than one thread here, okay? So you do have support to do that. Let now to conclude show you the previous example, okay? Okay, here is the second solution that uses condition variables and mutexes instead of semaphores, okay? So no semaphores, we reuse the data structure that we defined before, okay? And let's see at the resource manager structure. So it's similar to before, only we don't have semaphores. We don't have semaphores now, okay? But we do have condition variables, which happen to have the same name of the semaphore before, just these are not semaphores, these are condition variables, okay? No counter in them, okay? Also, I do have a mutex, which is not a semaphore again, it's a mutex. Okay? It's semantically, syntactically is different. Okay? Syntactically is different. And then you have the counters as before, the counter as before, the state as before. Okay? So, if before here we had a SEMT with the semaphore as SEMT for mutex, here we have condition variable and mutex for the mutex. Okay? The initialization is simpler, okay? So this is just something that you will see with Roberto Cavicchioli. Okay, this is just the semantic to initialize the condition variables. Okay. Okay, condition variable do not have again a counter in it. You don't need to initialize the counter of condition variable. You have no counter, right? And the mutex do not need to be initialized. The mutex is a mutex. So the first one that comes has it, okay? So here, start A, what does it do? Mutex lock is the same paradigm as before. Mutex lock, mutex unlock, okay? Mutex lock, mutex unlock. Simpler than before, okay? While, not if, while I'm in state sequenza nessuno, then I block myself. So one more A thread blocked, B thread can't wait, releasing the mutex before blocking. Okay? So this is the conditional variable, the condition variable, okay? This is the mutex to release before blocking and to acquire after being waked up. Okay? And when I woke up, I tentatively try again the mutex. When I have it, I continue. I decrease by one the number of blocked tasks, but I don't continue right away. What do I do? I recheck whether I'm still in sequenza nessuno, okay, or not. Okay? If I'm not in sequenza nessuno, I reblock again. Okay? If I am in sequenza nessuno, then only then I'm allowed to continue. Okay? While here. Okay? Not if. Then either I did not block here, or I've been woken up, then I move to sequence A, like before, and release the mutex. You see, it's a cleaner semantic. The only difficult part is this while here. Going on in the release phase, again, a clean semantic, the mutex lock here, the mutex unlock here, okay? So what is the responsibility of thread A to do? Oh, I erased it. The responsibility of thread A is to wake up one or more B threads. This is the instruction to wake up not only one B. So this is not a signal, this is a broadcast. Okay? The broadcast primitive allows you to wake up more than one thread at a time. Okay? This basically says, okay, this is my condition variable which has a number 0, 1 or more block threads. Wake them all up. Okay? No counter involved, just wake them all. Okay? Start B. Again, you can see that the mutex is locked here and unlocked here. While I'm in different state than B, I shall block, releasing the mutex and reacquiring it. Okay? Decreasing by one, increasing by one. Okay? Potentially needed to do that 1,000 times, or just one, or never. When I continue, and here I disable the mutex. Okay? And the same later, so it is the very same thing. Wake up A or C. When B is over, it needs to wake up either A or C. Okay? Shall I use broadcast here or signal? Why not broadcast? Exactly, we can have only one sequence active at a time. Okay? So in this case, I privilege the sequence A, or if there is no one else, I go to sequence C. Okay? And B, this is the very same before. Okay? Lock, unlock. Start C. Again, lock, unlock. If I'm different from sequence nessuno, I shall block. One more block, potentially blocking. One less block. Rechecking. If I'm still something different than sequenza nessuno, I reblock again, releasing the mutex. Okay? This instruction releases the mutex before. Otherwise, I can continue. I move to sequence C and release my mutex.
I'm sorry?
Yeah.
When I get the mutex after I enter the while?
Here you have the mutex, right?
Okay.
So assume that you are in a state different from sequenza nessuno, okay? So for instance, A is executing, or B, or C, or D, or whoever, right? So So then you enter here, one more block, and you perform this. This instruction automatically puts this code, release the mutex, and block.
Okay.
Okay? Now you're blocked here, you don't have the mutex. Someone else wakes you up, so this is thread C. So this, it can be B waking you up, or it can be D waking you up, or E waking you up. One of these wakes you up. So the first thing that you try, if you're scheduled, is to reacquire the mutex. Okay? If you don't, you just wait. As soon as you do acquire the mutex, okay, you see, okay, I'm running, so decrease this by 1 and recheck if I'm in sequenza nessuno or not.
Where did I get the mutex?
It's inside here, inside this instruction. This is what I wanted to tell you. So the release of the mutex and the reacquisition of the mutex is within this instruction. This is the very reason why you need to specify the mutex in the instruction. Okay? So it's built in the instruction. Okay? And going on. Okay? So it's essentially the same as before, right? So at the end of C, mutex lock, okay, the mutex unlock, probably later. Okay, so if there is a D to wake up, wake him up. Otherwise, there is a E to wake up, wake him up. Otherwise, go to state D or E and release the mutex. Start D, same as before. So mutex lock, mutex unlock. If I need to wake up, sorry, if I can pass, okay, I can pass only if I'm in D or E. Otherwise, I block, and again, this is a 1, okay? At the end of D is the same as before. E we already said. The rest of the code is exactly the one that we set, that we described before, okay? It's exactly the same as the one that we described before, okay? Therefore, I typically compile this with macro, so define semaphore or define mutex, so that you can conveniently decide which of the two solutions to check. Okay, they are absolutely equivalent. So core proved that the semaphore and the condition variable implementation are functionally equivalent. You can solve everything with any kind of paradigm/strategy. Okay, so typically I do this: define usa mutex or define usa sem. You can decide whether to use one or the other one. Okay, and you recompile it and you just use it for the other one. Okay. Okay, that's all for today. I will put this online along with the slides, and I'll see you guys tomorrow. A domani.